Okay. Yeah, so guys, look what you have here. You have the span of something, which means it's a subspace. Subspace of what? Well, all of these vectors that you're looking at in this list are in the capital W side of the picture. Right? See, here's your picture. You've got your vectors. This is like V1. This is like V2. So T of V1 is this one. T of V2 is this one. You're transforming those vectors. You're getting vectors on the W side, and you're just taking the span of those. So you're going to get a subspace of W. Let's try it on this problem. It's actually just very nice. So on this example, so on problem 6, what we do is we're going to take the span of, so what is everybody's favorite basis for P2 of R? 1x and x squared would be a great choice. So I'm going to take T of 1, T of x, and T of x squared, right? That's the formula for it. Real quick, before I actually do any of that, based on looking at this, would you be able to tell me that the dimension of the range of T is 3? Sorry?
You have polynomials of degree 2 and these two vectors.
They're polynomials of degree 2 or less. Of course, that is a three-dimensional space. But, okay, I'm going back to something we've talked a lot about tonight. If I give you 3 vectors, do they necessarily make a three-dimensional space? No, because they could be LD, exactly. So I'm going to make a list here, and whatever these 3 things are, they will span whatever they span, which is what we're calling this range of T. Okay, but they might be LD. Let's take a look. What is T of 1? I'm just going to calculate these 3 things here. T of 1. So I come back over here and I'm going to plug in 1 for my input. Well, so what do? I take the derivative of it, and I take a double derivative of it, and I've got these other things in there. What am I going to get, though? 0. Oh, there you go. Already you have something that's very LD, right? You're going to throw this one away, probably. Okay. Let's try x. So T of x. Well, T of x, all right, I take the derivative of that, I get a 1. So it's x times 1 plus 2 times, what's 2 derivatives of x? 0, right? So it's just x. So T of x is just x, right? It's just x. You with me on that? Okay. And then what about T of x squared? Well, T of x squared, I have to take the derivative of it. So T of x squared, I'm going to scratch work down here. It's x times 2x plus 2 times, what's 2 derivatives of x squared going to give me?
1. Multiple.
2, right? So I get 2x squared plus 4, right? 2x squared plus 4. These 3 polynomials span the range by the definition, basically. By the definition of the range. So I ask you, how do you find the range? You just simply take the span of whatever you get when you transform your basis. This problem happens to be polynomials, but you're going to see other examples that are going to be matrices or traditional vectors or whatever they look like. Doesn't matter. But then if I ask you, in part C, I ask you for a basis for the range of T. So this is a classic example. This is like problem 4.6, number 19, where it said, find a basis for the vectors spanned by, and it gave you that list of vectors, and we had to throw some of them away. It's like that here too, right? Are these, would anybody tell me that all 3 of these together would be a basis for the range? Oh, for sure not, right? Can 0 ever be in a basis? Throw it away. Throw it away. Doesn't do anything for you. Now what about the 2 vectors that are left? Would these be a basis for the range of T? They need to be Li. That's a great way to say it. And in the case of only 2 vectors, because now I only have 2 vectors left, do we have a quick way to eyeball it to say if they are Li or not? Right. So are these 2 vectors scalar multiples of each other? Can I take a constant times this one and get this one? No. So these 2 are Li. So a basis then, basis is the set x and 2x squared plus 4. There you go. And what would the dimension be? It would be 2, right? The dimension would be 2. The dimension of the range of t would be 2. Okay. So I kind of gave you a sneak preview of section 5.3 by doing this problem, but you know, I'm obviously going to go over it a bit more tomorrow. Are we okay with that? So the range of t, this is really the key formula you want to start learning. This is the range of t. These vectors here, they do span the range of t, but they might be LD. You have to, once you get your list, you have to throw things away potentially. Okay? You good with that? Let me show you another problem that has to do with linear transformations. Okay. I want to practice this stuff a lot because this is the newer stuff. But it ties into the older stuff too, so it doesn't hurt to keep practicing this a little bit more. And we'll do a lot more with it again tomorrow night. Let you guys watch the videos. I think you'll get this down. Okay, so here's another example. I'm going to go backwards and do number 5 on the handout right now. Okay, but here's what number 5 says. Suppose t goes from P2 of R to M2 of R is linear, and I want to assume that T of 1 is equal to -1, 2, 0, 0. T of x is, I'm sorry, not T of x, sorry. Okay, sorry. T of 1 is just that. T of x plus 1 is -3, 0, 2, 1. And T of x squared plus x plus 1 is 3, -2, 0, and 1. Okay. Here is the question. Find T of ax squared plus bx plus c. Okay, so this is a little bit different problem. The amazing thing is, I only told you T of 3 things, and now I'm saying find T of anything. And this problem is very different from the last one because in this problem, I'm not asking you to show that T is linear. I'm actually telling you that T is linear. So this problem is supposed to make you feel like linear transformations are awesome. If you have something that you know is linear, it's a powerful assumption. The idea is, well, gosh, in order to figure out T of any polynomial in P2 of R, I'm only going to need to know T of these 3 things. Do you kind of see, does anybody have an idea of sort of how this works? Erwin?
So you would first distribute the transformation to like T of ax squared plus T of bx plus T of c.
Okay.
And you would pull out the a and the b and you get T of x squared.
This is absolutely the trick, guys. Right? Linear transformations, and when you pull out a c, you get just 1. Linear transformations respect linear combinations. They respect addition and they respect scalar multiplication. So if I know what T of x squared is, and if I know what T of x is, and if I know what T of 1 is, then I know T of anything. Right? Well, let's see. How are we doing on that? T of 1 I was actually given. So that'll be easy. We'll just plug that in. T of x. Did I give you what T of x was? I did not give you T of x. Is there a way to get it?
Subtract this.
Look at this, guys. I gave you T of x plus 1, and I gave you T of 1. Remember, T respects all of these algebraic steps. So if I take this one minus this one, I'll figure out what t of x is. So t of x, so I'm just going to make a note here, t of x is just t of x plus 1 minus t of 1, right? That's really the key here. T of x is just t of x plus 1 minus t of 1. You can just subtract, just like that. T respects that. Okay, so I'm just going to have to take the second matrix. This is what Erwin is saying. I just have to take the second matrix minus the first matrix. The second matrix minus the first matrix. If I just do that subtraction, I'm going to get negative 2, 2, and 1. Okay? That's t of x. So far, so good? Everybody see that? What about, so what else do I need? I've got t of 1, t of x. What about t of x squared? Does anybody see how I can get that one? Exactly. This one minus this one will give me exactly the x squared. That's exactly right. So t of x squared is going to be 3, negative 2, 0, 1 minus negative 3, 0, 2, 1. And when I subtract that out, I'm going to get 6, negative 2, and 0. There you go. There you go. So we've got that. And now, what I want to do is just write down the final answer. That's all. We're ready to do that already. Okay, so t of ax squared plus bx plus c is just, let's see, it's a times the first matrix here, 6, negative 2, 0. That's the t of x squared matrix. Plus b times the second, the t of x matrix, which was negative 2, 2, 1. Plus c times the t of 1 matrix, which was given negative 1, 2, 0, and 0. Okay? And that's actually, that's a perfectly good final answer for what t of ax squared plus bx plus c is. That works. If you want, and I would like you to do this because I'm about to ask you a follow-up question, you can obviously compress this all together into one matrix. It's one 2 by 2 matrix, right? What I can do is I can just look at the upper left corner. The upper left corner, I have 6a minus 2b minus c. Right? Everybody see what I'm doing? I don't have to do this. I could just stop at what I have already. I just want to show you what you get here. The upper right corner is what? Negative 2a minus 2b plus 2c. And then the lower left corner is negative 2a plus 2b. And the lower right corner is the really easy one. It's just b. You're inputting a quadratic polynomial, and you're outputting a 2 by 2 matrix. Make sense? Okay, so then now that you guys are really good, I know I've only done like one example, but I want to find a basis and dimension for the kernel and the range. I'm going to go back to that again. Okay? This is a great way to tie stuff together. So let's find a basis for the kernel of t. This is also part of the question. Can anybody remember? Oh, this is going to be easy. Can anybody remember how we find a basis for the kernel? Or how do we find the kernel?
Everything that goes to 0.
Say it one more time.
Everything that goes to 0.
Right, it's those inputs that get killed, right? So in other words, I want to know which ax squared plus bx plus c's end up getting killed here. And getting killed means I have to get 0, 0, 0, 0, right? And the process was you set t of v equal to 0 and solve for v. That was my procedure I gave you a little bit ago. Well, take a look. If you set this equal to 0, okay. Imagine that you set this answer here equal to 0. Can you guys look at that and tell me what's going to happen? Each corner of the matrix has to be 0. So how's that going to work when you solve it out? Can you do it in your head?
Everything has to be 0.
If you look at the lower right corner, B is going to be forced to be 0. And then as soon as I put that into the lower left corner, I also find out that A has to be 0. As soon as both A and B are 0, I can go up to the top part and figure out that C is also 0. Guys, the only vector that gets killed is the vector that was already killed, which is the 0 vector, right? The kernel of T is actually very, very small. It has only, I mean, the 0 vector has to be killed. But it turns out that that's the only vector that gets killed. So it turns out, okay, so I don't know if I've talked about this, but this is like the trivial vector space. You remember the vector space moon that we did like ages ago? This is like the moon vector space. There's only one vector. All I can do is add it to itself. Okay, I can add this to itself. I can scale it, multiply it. Right? It's so small, it's tiny, there is no basis. Right? It's kind of a trick question. There's no basis. The dimension is 0. Okay, so the dimension of the kernel of T in this example is just 0. That's basically the gist of it. Okay, and the kernel, the basis, I'm just going to say does not exist. There really is not a basis for the trivial vector space. You can't really have one. Because as soon as you have a basis vector, then you've got like all multiples of it, so you have this huge space. We don't have a basis here. It's kind of a trick question. All right, everybody okay with that? Okay, maybe we're getting a little more comfortable with this kernel range idea. Let's find the range. Let's do the range with the same problem. Okay? Let's find a basis and the dimension for the range. Okay, so basis and dimension for the range of T. Okay. Let's remember how that works. What do we have to do? So for the range, if you remember, the range is the span of T of a set of basis vectors for V. Okay, so this one's easy because it's the same as before. What basis for V would you naturally use?
X squared.
Exactly. So it's the same natural choice for basis as what we had before. Right? Okay, so this is going to be the span of, oh, and look at that. T of x squared, T of x, and T of 1, we already figured them out. T of x squared was this one, right? T of x squared is 6, -2, -2, 0. T of x is, oh, I erased it. What was T of x? Oh, it's -2, -2, 2, and 1, I think, right? And then T of 1 was given here. I still have that one on the board. -1, 2, and 0, and 0. Okay, guys, again, this is what the range of T is. Does it automatically mean that these are a basis? No, because again, this is like a list of vectors that span your space. You have to check if they are LD or not. Because if these are linearly dependent, you better start throwing them away, right? Your basis can't be LD. So we have to check if these are LD or not. And this time, maybe it's not so obvious. I think on that other problem where we had like these were the 3 polynomials, it was obvious we needed to throw this one away, and then these 2 were good, right? This one's maybe not as clear. I can't just look at this and see, oh, clearly this one is like doesn't depend on the other 2. I can't actually see that. So this would be an example where you actually have to go to the work of like putting those vectors, you know, doing the old-fashioned linear independence check. So the first vector, I would just put it in the first column here. And the second vector in the second column. the third vector in the third column, and I would just augment with all 0. Like that, right? And I have to row reduce that. And figure out whether I get pivots in every column. Oh boy. That doesn't look too funny. Hopefully I won't give you one this bad. This looks messy to figure this out. Okay, I'm going to try and cheat and do it very fast. I'm going to take the third row. Remember I said we can get a little quick with our EROs. I'm going to take the third row and put it on top, but I'm going to change the signs and I'm going to divide through by 2. So 1, -1, and then 0. So that's this row. I'm just going to put that at the top because it's a simple row. And then I'm going to put the fourth row in the second position. So I'm going to do that. So far I'm already looking pretty good here. And then I have these other 2 rows. Let me do the -2. The -2, -2, 2. I'm going to put it next, and I'm going to change its signs to 1, 1, and -1. Okay, and then the fourth row, I don't even care. Because you know what? What's going to happen is that when I take suitable multiples of the first 2 rows and add them to the third row, I'm going to get a pivot there. So although it was not as obvious this time, just take my word for that part. I don't want to get strung up on EROs right now. Although it was not as obvious this time, these 3 matrices are actually Li. Because how do I know that from the matrix? Again, the point is there's no unpivoted column. We're always looking at unpivoted columns, even if we get all zeros here. Rows of zeros is not the key. You're not looking at that. You really want to look at columns and where the pivots go. So there are no unpivoted columns to the left of this bar, which means that there are no free variables, so there are no dependencies. So these guys are not only a spanning set for the range, they are Li as well. So therefore, this is your basis. These 3, this is your basis right here. You don't have to do any more work. And what's the dimension? 3. You guys want to know a little secret? I'll tell you this because this will help reassure you. For every single linear transformation problem that you ever do, the dimension of the kernel plus the dimension of the range, I will write this down tomorrow night. The dimension of the kernel plus the dimension of the range always has to add up to the dimension of V. What's the dimension of this vector space? 3. What was the dimension of the kernel?
0.
We had gotten 0 already, so actually, amazingly enough, we already knew, if we know that fact, that the dimension of the range must be 3. So we actually, through the back door, knew that these were going to be Li to begin with. Because if I had to throw one of them away, the dimension would have dropped to 2 or 1 or something, and then they wouldn't have added up right. So this is a fact you don't know the reason for yet, but the dimension of the kernel plus the, maybe I should write it down, it's so helpful. The dimension of the kernel plus the dimension of the range always adds up to the dimension of V. Very, very nice fact. Okay? Awesome. Okay? Everybody all right with that? I have now done 5 out of the 8 problems on my IQ sheet. The other 3 problems that I haven't done are kind of similar to things we've been talking about, though. So one of them is just, I just gave you a matrix and said find a basis for the row space, column space, and null space. So if you know how to do that, it's kind of a standard problem. Another one is, well, I gave you the span of a set of vectors and said find a basis. So you have to check them for linear independence, right? And that's actually kind of what the other one is about also. So I don't feel that I have to go through those now, but I will, if you guys want more practice. I'm happy to stay, a little bit longer and just finish up a couple more problems. Or I can just let you have at it. Maybe you've had enough for tonight, you want to go work on some stuff on your own, and then you can read these on your own and study them on your own. I'm really flexible. It's kind of, what would you guys prefer that I do? You want me to show you a couple more examples? Or are you like burned out? It's like not going to do you any good at this point. Because I'm happy either way. It would be more examples of the same kind of stuff, so it's not like I have omitted something really super important. I mean, there's a lot of things you still need to, you need to practice more of those problems of showing something as a subspace. You have to practice more of that. Getting your head around this linear independence, spanning set stuff, that's important to keep practicing that in lots of different contexts. The kernel and range stuff, you may not feel 100% solid yet, but I'm going to go over that tomorrow night. Of course, that's the main theme of tomorrow night is talking about, kernel and range and linear transformations. So you'll get, basically that's like a review of that stuff, which will combine with the chapter 4 stuff. I didn't really go over the Graham-Schmidt stuff, the orthogonal sets, orthonormal sets, and all of that, inner product axioms and stuff like that. So that's something I didn't really do. I don't have anything on that on my sheet, but I just don't. So if there's questions about that, I could answer them. What do you guys? What's your pleasure?
I'll stick around if you more calls.
Okay. Other people want to see you do a few more? Yeah, why not? Okay, I'll do a couple more problems. Practice a little bit. Why not? I'm having fun. I'm going to go out of town for 10 days on spring break and not talk about math the whole time. I need to get my fill of it now. Yeah, it doesn't hurt to practice it. I mean, you can kind of this is like part of your studying for the test, so why not? As long as you're not burned out, I don't mind. Go a little bit longer here. Okay, so let's do another problem. Okay. Let's find a basis for V equals the span of 1 minus 2x plus 3x cubed, comma, 2 minus 5x minus 3x squared plus 6x cubed. I think this is off of an old test, actually. Comma, the next one is x plus 3x squared, comma, the next one is 2 minus x plus 4x squared minus 7x cubed, comma, one more. We're sorry you asked, right? 5 minus 8x plus x squared plus 2x cubed. Wow, 5 polynomials. Okay. What, I didn't tell you in the question, what's the big vector space that everything's in right
PD.
here? P what? 3 of R. Very good. You have to look at the powers of x. You see that there's nothing of degree 4 or more. Okay. So, real quick question. Can these polynomials be a basis for V? Oh, you know what? This is very bad. I'm sorry. I don't want to call this, these are not both V, right? So don't call this V. This is just the vector space. P3 of R is what they all sit in. Is V, which is just this span, are these 5 polynomials going to be a basis for it? No. They can't be, right? You just know immediately, because what's the dimension of P3 of R? 4. Only 4, right? If it's only 4-dimensional and I give you 5 vectors, that's too many, right? K is bigger than n. So that's too many vectors. So you know that these are LD, right? In fact, you don't really know, there could be lots of dependencies lurking